Good morning. We are going to teach today on game theory because this is a continuation of what we have done in the erstwhile or the previous lecture on game theory. Now, this particular lecture is in fact on who plays and how the strategy is being formed. Because in the last lecture we said who plays when and the simultaneous and sequential play was being introduced. So now we are going to discuss that a little elaborate. Let me come to the sequential game example. So sometimes game has more than one Nash equilibrium and it is hard to say which is more likely to occur. Now when such a game is sequential, it is sometimes possible to argue that one of Nash equilibrium is more likely to occur than the other. So we have already seen an example which we have done, that is the up and down and left and right strategy game in the beginning of the previous lecture. So let us discuss the lecture based on that sequential game. So now you have player B has strategy of left and right, player A has strategy of up and down. Now we have two Nash equilibrium 3 9 and 2 1, and then the unlikely play like both 1 8 and 0 0. So if your UL and DR are both Nash equilibrium when this game is played simultaneously, and we have no way of deciding which equilibrium is more likely to occur. So in the simultaneous case you have actually an uncertainty of which one is the best, or then these are two Nash equilibrium, it can happen, either of this can happen. So there is no definiteness that which one people opt. But in the sequential game you can actually go really with a conclusive result in that sense. So that is what is actually the beauty of a sequential game. Suppose instead that the game is played sequentially with a leading and a B following. Okay, so A is the first mover and B is actually a follower in this case. So if that is the case, then if A moves to up, then B has a strategy of left and right, where left is actually desirable as far as this particular in a straight sense. So if A is actually moving, and if A move uh, you know down, A play down, then definitely we also has the strategy not to actually play any left but only right. So uh, this is actually in fact comes with this particular aspect. So we write the same game with an extensive form. An extensive form is actually a game tree. Okay, trees are actually connected with the nodes, so we'll see that. So the next one is actually a sequential game. The same game can be actually drawn in this is a sequential game. So A is the first mover in this case, there is no simultaneous. So simultaneous win, then two trees will come simultaneous. So in the sequential game it is possible A is the leader, so A is actually having two strategy up and down. If A goes for up, then B has actually follower, then B choose accordingly, and of course B chooses left. In that sense both will gain. Okay, so if mm, in the second case if A moves to down, then B also has the strategy and B plays definitely right. So A plays first, B play in this case it is pretty clear, and UL is a Nash equilibrium. In this case the up and is a Nash equilibrium, and DR is also a Nash equilibrium, which is more likely to occur. Now if A plays U, then B plays L, A gets 3. Okay, if A plays D, then B plays R, A gets 2. So in that sense UL is the likely Nash equilibrium in this particular understanding. So a series of nodes linked in a sequence, non-terminal nodes, not an endpoint. Terminal nodes indicates that game is over. So these are actually the interesting point as far as the game trees are concerned. So as I said, branches represents action, and the loops, there should not be any loops, should not be any loops. That is very important. Loops, that is cycles, are not allowed in game trees. Okay. Now, what we do is actually we'll look into the two crucial element of extensive form games. One is timing, the other one is information. These two things are very, very important as far as the game theory is concerned. So, timing of an action that players may take is a very important one, and information they have when they must take those actions. So, this is called the information set. Okay, so we will discuss one by one. Let us first talk about the tail, this information case time. Tale, let a tale of two films, that is 1998, Disney. Okay, Disney has A Bug's Life, DreamWorks has Ants. Okay, now a model, that is set of players Jeffrey Katzenberg and Michelle Eisner. Okay, now Michelle Eisner is actually Disney CEO, set of actions for each player, etc. Now you have J, that is you have K and you have E. Katzenberg and Eisner is the two player, and you have two movies, right? Tale of Two Films, 1998. Okay, that is Disney's A Bug Life and DreamWorks Science. Okay, now let's look create a extensive form. Katzberg's first move. What is Katzberg's first move? Katzberg leave or stay. Initial node. Okay. Now from that, suppose Katzberg leave, then produce a bug's life. That's if Katzberg leave, then Eisenberg produce a bug life. Okay. Uh, then that leads to Katzberg produce ants. Okay. This is one way. Now, again, in that sense, Katzberg not to produce ants life. All right. At the same time, if Katzberg leave, Eisenberg is not actually producing any film that is A Bug's Life, then Katzberg also can produce ants. Okay. Okay, so this is also another possibility. So A Bug's Life being produced by Eisner, but Katzberg produced ants. So without even producing this, cats can produce ants, or cats just refrain because nobody produced anything. So in that possibility also there. So Eisner is actually not produced anything. Therefore, cats also not produced. End of the story. All right. So if this is a sequence, then in this case there is a information node. That is, if Eisenberg produce a bug life, then again there is a possibility that cats come and produce ants. If it is not, Eisenberg is not producing bugs life, then also there is a possibility that cats comes and produce ants. So these two information nodes is even the result of this sequence in that sense. So information sets is a very crucial one. That is, information set summarizes a player's knowledge of prior moves when she must decide. If there are more than one nodes in an information set, a player knows that she is in one of the nodes in the information set but does not know which one. So either on the in that earlier is either in the up or in this down. Information sets containing only one nodes are referred as a singleton. Now, if you have only one node, then it is called the singleton. If you have more, especially two, then doubleton, and if more than that, you have multi. So, adding terminal nodes in this case, uh, that is these 2 points. You can produce ants, you can, or you can actually, if be without producing, that is a bug's life, without producing a bug's life. If you produce cats, then your pair would be different. Now if you produce, then you have another possibility of release early, okay, or not. So there are other possibilities, extensive possibilities, which we can basically incorporate. All right. Same can be basically incorporated. Now in that sense, simply you can add some value. If you release early, you will get more money. If you are not releasing early, then you won't get that much of money. The other, in this case, produce bug life, produce ants, then there is two possibility. The produced bug's life can be early or can be late. So cats can also release early or late. Again, if he can produce, if he is not actually mm, producing ants life, then bugs life being produced, then he or listener gets 140, then cats gets nothing. Whereas if it is listener is not produced, sorry, not produced a bug life, and cats produces ants life or ants, um, then the whole benefit will be accrued by ants would be greater, double, because the life, money, etc. So if one person stay, and so these are actually kind of different um, results in which one can see what labeling branches differentiating between n and n dash conformity with an information set. Okay, so there are different kinds of understanding which we can derive out of it. In the beginning, we try to point out a crisis, which is Cuban Missile Crisis. Let us discuss that wartime or warlike situation, how countries manage this warlike situation. There are different questions people ask about the Cuban Missile Crisis. Why did the Soviet Union attempt to place offensive missile in Cuba? Or why did US respond with a blockade of Cuba? Or why did Soviet Union decide to withdraw the missiles later on? So all this can actually again be seen as a game interaction. Suppose this is being placed in an extensive form. Let us begin with this challenge. USSR placed means they are challenged. The USSR can actually have two options. Either they can challenge or just don't challenge. So if USSR is not challenged, then that is what is called the status quo. It is being maintained. There is no issue. But in this case, if USSR is posed a challenge, then United States has two strategies: either resist or not resist. If they not resist, then concessions. Okay. Now, if they resist, then there is two possibilities, simultaneous two possibilities for the Russians case, because it's a sequential game in that sense. So they can either push for war or just backtrack. Okay, back down from this kind of. So press for war, not press for. So if they press for war, war is the result. If they don't press for it, then there is no war. So this is what is actually the kind of crisis which we can immediately draw in an extensive or um, extensive game tree. Now adding uncertainty. If there is uncertainty, we model this by adding nature or chance as another player. It does not have payoff. It chooses different type. For example, two type of defenders. Resolute type prefers war to concession. So irresolute type prefers concession over war. Now some people likes war, some people don't like war. If challengers can observe defenders type, then you have different kind of understanding in this particular case. So let us have the thing. Then you have yen, then you have resolute behavior and irresolute behavior. So if you resolute, then you challenge, not challenge, then that ends. If you challenge, then again you have defender's move comes. So defender has 2 points. Either they go for a consent, that is they accept it, or they challenge a retribute or retribution act of them. Again it challenges, it push to the war, or it is not pushed to backtrack, okay, back down from this thing. Irresolute case also, you may challenge and that is results this thing, or the respondent has defender has 2 point, go for war, challenge, retaliate, or go forward, or don't backtrack. So all this is having the two kind of situation, two different possibilities in this case. Now in this two type resolute and irresolute case, you have two information sets. See, that is challenging. Again the after challenge, again for the defendant is also having two information sets, challenge, whether go for challenge or not. So this is what is called two information sets as far as this particular uh, game, extensive form of game is concerned. Now there are other examples which popular examples textbooks talks about. One is rock paper scissors example, simultaneous move game. This is a simultaneous move game. Normal form represent in the following: that player 2 and player 1 has different set of actions. So one can go for rock paper scissors. So rock paper scissors for all of them. If all of them goes for simultaneously rock paper scissors, then their uh, of course their you know res- uh, payoff is actually 0 0 0 0 0 0. If one person go for rock, the other goes for paper, then 0 again scissor 0. It's a zero sum game in that sense. Okay, all right. Now if you play the same in the sequential form, you have this particular thing, and if you do the same in the simultaneous mode, you'll also have this thing. So I have already discussed this, right? So you have an information set here, there is no information, okay, that happens simultaneously. Now if two can observe, if one chooses rogue but not otherwise, then also there is an information. So one is actually an information, the other doesn't have an information set. Okay, now let's move to the truth game of the same. An uneven coin heads 80% of the time to players 1 and 2. Player 1 flips the coin and observe the result. Player 1 announces head or tail. Player 2 hears one's announcement but cannot observe result of the actual coin flip. 2 announces edge or tail. Payoff is that 2 receive $10 if answer is true, and 0 otherwise, and 1 receive 20 if 2 announces head, and an addition of $10 if 1 tells the truth about the coin flips. Okay, so if that is the thing, you can simply write it again in the head tail example, and immediately you have an extensive game forms like this. In the second case, you have actually an information set, as we have said. So the payoff to receive $10 if answer is true and 0 otherwise, and one receives 20 if two answers said, and an additional 10 if one tells the truth. So that is what is actually being depicted in this extensive. Again, advertising or exit game also has a similar situation, so one can refer from the textbook. There's so many beautiful textbook. You know, for an introductory game theory, you can read Oxford introductory thing for a preliminary understanding, which was Ken Binmore's one. But Ken Binmore had a beautiful book, which is a bigger one, a voluminous work, which is also on a game. Or you can refer Osborne's theory of games, only that is for an advanced kind of learning in the game theory. Otherwise, you know, for preliminary things, there is a chapter in you know, Polar variant, and there are many microeconomic text carries game theory lessons, so you can very well refer there, and you will see all this example. So advertising game is there, so there is an interesting game which is called Ultimatum. So player 1 wish to sell a painting to player 2. Alright. One want to actually sell. Painting is worth nothing to player 1 but 100 to player 2. Seller makes a take it or leave it offer. If buyer accepts the price, trade at this price. Otherwise, both parties obtain nothing. So this is what this. So you have a painting. That paintings. So in that sense, it is only the trade take place, then the gain comes. So ultimate gain is something very interesting. One has to look into really of that kind. See, the trust games in a simple sense of a trust game, especially in the business, when you are talking about so much interdependence, there is no interdependency between the interaction, then uh, you may not develop any trust, because interdependence, trust is interdependent. So if you don't have any trust to others, there cannot be any business in the real world. Therefore, such kind of games tells you that, you know, there won't be any business at all, and there won't be any economic activity. So this is how the trust game is an interesting one. One learns in law and economics if you're interested in. So I'm leaving that right now. So again, definition for an in-person extensive form game consists of the following. This is what is actually the details of what we have said earlier, demonstrated. A finite game tree composed of nodes and branches, which I have already said, division of nodes and overplay and center. Endpoints, probability distribution for each chance move, division of each player's nodes into information sets, sets of outcome. This is all common knowledge to all players in that sense. So strategies also we have seen, and for the sake of definition, it is given in a nutshell that strategy is a complete contingent plan of a player in the game. Complete contingent describes what she or he will do at each of her information set, and writing strategy for a player I is actually find every information set for player I. At each information set, find all actions, find all combinations of actions at these information sets. Now, if that is the case, let us actually call our own example, which start with the player A and B is left and right and up and down. Up and down and left and right strategy. Okay, and we see that whether these strategies are pure or mixed. Another set of classification which we are going to deal with. So this is our original example once more. So suppose again that play is simultaneous. We discover that the game has two Nash equilibrium UL and DR. Player A has been brought of a choosing to play either up or down but no combination of both. That is a playing purely up. Either you go for up or you go for down, or you are left or right. So this is what is called a pure strategy. So U and D are players A's pure strategies in that sense. Similarly, for L, that is left, or R for B is also a pure strategy. So the discussion which we had advanced is actually called pure strategy. Consequently, UL and DR are pure strategy Nash equilibrium in that sense. That is, your L and U, 39 and 21 is pure strategy. Must every game have at least one pure strategy Nash equilibrium? The question is that do we necessarily have to have a pure strategy in every game? There are certain games we may not be having it, but there are certain games we may have it. So there is no if there is no demand that it should be pure Nash equilibrium. So that is the thing which you have to keep in mind. What does it mean? It can be the mixed strategy also, mixed Nash equilibrium. But only thing is that if a game is a finite game, definitely you may be having a solution. That is the it can be either pure or mixed. All right, that is what is actually it means. So if you change the game of left and right in the numbers and all, you will get different. Here a new game, that is 1 2 0 4 0 5 3 2. Here is a new game. Are there any pure strategy Nash equilibrium for this example? Now in this case, you will Nash equilibrium answer is no. 1 and 1 2 is not actually a Nash equilibrium. Why? Because one if you play up and the other play left, so if you play up, the other is not necessarily going to play left, because uh, for him, uh, if he plays left, then you will be actually moved towards D. Why? Because left means 0, the other is actually this thing, and vice versa. So in that sense, your up and right is also having no Nash equilibrium. DL is also not actually having a Nash equilibrium, because you move on. 0 is not desirable for that person, therefore there is no Nash equilibrium. Either the way, in all these numbers, as a strategy, you don't have a pure strategy. Okay, this is based on pure strategy. So the game has no Nash equilibrium in pure strategies. Even so, the game does not have a Nash equilibrium, but in a mixed state. Again, the same is also has whether this is having a mixed strategy Nash equilibrium. Instead of playing pure up and down, player A select a probability distribution like pi u 1 minus pi u, meaning that with probability pi u, player A will play up and probability 1 minus pi u will play down. So player A is mixing over the pure strategy up and down. The probability distribution of pi u 1 minus pi u is a mixed strategy for player A in that context. Similarly, for B also have select a probability distribution which is pi L and 1 minus pi L, meaning that with probability pi L, player B will play left, and with probability 1 minus pi L will play right. So player B is mixing over the pure strategy left and right. So the probability distribution is pi L 1 minus pi L is a mixed strategy for player B. So if that is the case, then same example which we see earlier can be understood in this following sense. The game has no pure strategy, as we have already said, but it does have a Nash equilibrium in mixed strategy. How it is computed? Let us look into it. Now, as I said, this pi L and 1 minus pi L for L and R, and pi U and 1 minus pi U for up and down is simple to calculate in that sense. So let us calculate. Let's take this first one. If B plays left, her expected payoff is 2 pi u plus 5 1 minus pi u. Alright. So this is what is actually the probability. Again, if the right is the case, then B plays right, her expected payoff is 4 pi u plus 2 1 minus pi u. Alright. Now if 2 pi u plus 2 5 1 minus pi u is greater than 4 pi u plus 2 1 minus pi u, then B would play only left. Okay, but there are no Nash equilibrium in which B plays only left. Okay, that means if pi 2 pi u plus 5 1 minus pi u is less than 4 pi u plus 2 1 minus pi u, then B would play only right, but there are no Nash equilibrium in which B plays only right. This is the case. So for there to exist a Nash equilibrium, B must be indifferent between playing left or right. So that means you should be indifferent rather than you go for one strategy. So to that indifference means there is only a probability, that is 2 pi u plus 5 1 minus pi u, which is equal to 4 pi u plus 2 times 1 minus pi u, which gives a result, that is pi u is equal to 3 by 5. Okay, now we can recalculate the same with the case 3 by 2 is your probability of playing up, and 2 by 5 is actually probability of you playing down. So now it is a probability incident. Now same can be applied for the left and right strategy. If A plays up, his expected payoff is 1 times pi L plus 0 times 1 minus pi L, which is equal to pi L. Okay, if A plays down, his expected payoff is actually 0 times pi L plus 3 times 1 minus pi L, which is equal to 3 times 1 minus pi L. Okay, if pi L is actually greater than 3 1 minus pi L, then A would play only up in this case, but there are no Nash equilibrium in which A plays only up in this case. Again, if pi L is less than 3 times 1 minus pi L, then A would play only down, but there are no Nash equilibrium in which A plays only down in this case also. So for there to exist in Nash equilibrium, A must be indifferent between playing up or down, that is pi L, which is equal to 3 1 minus pi L. So if that is the case, then it gives you pi L, which is equal to 3 by 4. Okay, so we can recalculate the same with the case. Alright, so now for your playing left is 3 by 4 and playing right is 1 by 4. Okay, so that the game's only Nash equilibrium has A playing the mixer strategy 3 by 5, 2 by 4, 2 by 5, and has B playing the mixer strategy 3 by 4 and 1 by 4. So now you have two strategies. If that is the case, the payoff will be 1 2 with the probability, that is 3 by 5 times 3 by 4, which is 9 by 20. Alright, the payoff will be 0 4 with probability, that is 3 by 5 times 1 by 4, which is equal to 3 by 20 in that case. Okay, for the other column, that is payoff will be 0 5 with probability of 2 by 5 times 3 by 4, which is 6 by 20 in that sense. And the final one is 2 by 5, that is 3 2 case, probability would be 2 by 5 into 1 by 4, which is 2 by 20. If this is the case, see, you look into 9 by 20, 3 by 20, 6 by 20, and 2 by 20. So which one you will play? by the calculation of the probability, you'll go for the 9 by 2 case. That is the mixed strategy equilibrium, which was given as expected Nash equilibrium payoff. So that is 1 times 9 by 20 plus 1 by 3 by 20 plus 3 is 0 by 0 times 6 by 20 plus 3 times 2 by 20 is equal to 3 by 4, as we said. Okay, now for the other B's expected Nash equilibrium payoff is actually 16 by 5. That is 2 times 9 by 20 plus 4 times 3 by 20 plus 5 times 6 by 20 plus 2 times 2 by 20, which gives you 16 by 5. So in that sense you have already talked about. So a game with a finite number, what is the conclusion? As in the beginning I pointed, a game with a finite number of players, each with a finite number of pure strategies, has at least one Nash equilibrium. So if the game has no pure strategy Nash equilibrium, then it must have at least one mixed strategy Nash equilibrium. So that means if the game is a finite one with their players and the moves, then definitely there should be a Nash equilibrium. That can be either a pure strategy Nash equilibrium or a mixed strategy Nash equilibrium. Alright, so this is what is actually the whole topic of game theory which we are going to cover today, especially as part of the microeconomics. So if you thoroughly go through this, then things would be greater. So thank you for listening me, and I am so glad that you enjoyed the lecture. Thank you once again.